Hey, welcome back. This is Calc 2. We're talking about growth and decay in this section. And what we're going to do is look at the most simple fundamental model that you'll see in differential equations. And you've probably seen it before in your physics class, in your biology class. Okay, so let's take a look at growth and decay. Before we get too much into it, we need to be able to solve just kind of simple differential equations. We'll talk more about the methods for solving differential equations in 6.3 and 6.5. But we want to introduce it so you have some tools at your disposal. So section 1, solving some differential equations. We'll just say DE. And let's take a look at example 1 and see what they have for us, right? Okay, so they have the differential equation y prime equals 2x over y. You could rewrite y prime as dy over dx, okay, and that equals 2x over y. And then what we're going to do, and this differs a little bit from the book, but it'll foreshadow what we're going to do in the 6.3 eventually. I want to get all the x stuff on one side and all the y stuff on the other. So I'm going to move the dx to the right side and move the y to the left side. So if you multiply both sides by y, you'll have y dy. If you multiply both sides by dx, you'll end up with 2x dx. Okay? And then we're going to integrate both sides of this equation. Technically, what you see in the book is what you're really doing. So in the book, the second step, they just multiply both sides by y, and then you have 2x. And then they integrate both sides with respect to x. So if you were to rewrite y prime as dy over dx, and then give me a little space so I could write the dx on the left-hand side here. You'd have the integral of this with respect to x, and on the other side, the integral of that with respect to x. It's just like if you square both sides of an equation, or if you add something to both sides of an equation. Now you can basically integrate both sides of an equation. So here, you know, the dx's would normally cancel on the left, and you basically just end up where I was. Okay, so that, you know, I'm sort of not doing exactly like what the book does, but this is where we're headed in 6.3. Okay, and that's called separation of variables. Once you have it in this form, you want to integrate. So you have y squared over 2 on the left side, and then there should be a constant, but we just put all the constants on the right. Okay, so you need not worry about that right now. 2x squared over 2 on the right here, and then there's my constant. Okay. At this point, what the book does is they kind of want to get rid of all the fractions, and I think that just might have been because back when they were writing books, not having fractions took up less space. So here they're going to multiply both sides by 2, so 2 over here, and then 2 over here. And then you get y squared equals x squared plus 2c. This constant thingamajig here is basically will absorb any other constant. It gets multiplied. It wouldn't absorb a variable, but it will absorb this 2. Okay, so you would have, and I lost a 2 there, sorry. We're going to rewrite it as y squared equals 2x squared plus c. Okay, technically you should kind of label this as a different c value, but at the end, ultimately you'll just end up with this c thing, so it doesn't really matter too much if you're not worried about being perfect. Anyways, in the last step, you see they put the 2x on the other side. Why do they do that? That's because this is one of your conic sections, right? This is a hyperbola right here. So they like to put it in a form that's familiar. Note if you would like take the square root on both sides, that would be kind of annoying because it would be like plus or minus square root of 2x squared plus c. And I think this form right here is just prettier, right? We don't have the plus minus thing. And this form here would be explicit. So you have y equals something, it's called explicit. This form is called implicit. And so sometimes the implicit form is better because it's just more recognizable if you're playing around with hyperbolas all day long. Okay, so anyways, that's our general solution for this problem. And yeah, okay, so hopefully that kind of gives you some sort of introduction to it. Let's do they have any more examples? No. Let's take another example, maybe from the homework here, and see how that goes. So let's try number 2. We have y prime equals 17 square root of x times y. So again, I'm going to do this, what they call separation of variables. I'm going to rewrite y prime as dx over dy over dx. And then over here I got 17. Rewrite square root of x is x to the 1/2. So I'm going to be integrating it. So I want the power rule, you know. So anyways, I always like to leave the constants on the right with the x stuff, and then I'm going to move the y to the left and the dx to the right. So I'll have dy over y equals 17x to the 1/2 times dx. Okay. Then integrate both sides. So on the left, it's ln absolute value of y. On the right, we'll have 17x to the 2/2 plus 1/2 is 3/2. Divided by 3/2 is the same as multiplying by 2/3. And then plus our integration constant. Here, that ln of absolute, I mean, as it sits, it's implicit, right? It's not y equals. And sometimes it's better just to leave it alone. But in this case, we could actually solve for y. And what we're going to do is exponentiate both sides. Okay, so I'll have e, and let me just write it out just for the sake of instruction. I have e to the ln of the absolute value of y. On the right, I have e to the 34/3 x to the 3/2 plus c. Okay. On the left here now, the e and the ln are inverse functions of each other, so they'll cancel each other out, and you'll just be left with the absolute value of y. On the right, I'm going to rewrite it using one of our exponent rules. So I can rewrite this as e to the 34/3 x to the 3/2 times e to the c. Okay. Then I'm going to drop the absolute values. But if you drop the absolute values, you have to replace it with a plus or minus on the other side. Okay. Then I'm going to rewrite the order as e to the c times e to the 34/3 x to the 3/2. And then I'm going to replace this entire thing with a constant. Okay, so it'll look a little nicer now. Y equals c e to the 34/3 x to the 3/2. I know I wrote a 4 there, but it should be 3/2. Okay. Okay, so let's zip over here and put it in and see if it's right. And hopefully is that a 3? I hope that's a 3. And it looks like it's right. Okay. Let's do at least one more of those, right? Let's try number 4. I don't think they do enough examples in the book. So xy plus y prime equals 184x. I'm going to isolate the y prime. So y prime equals 184x minus xy. I'm going to factor out the x on the right-hand side here. So I have x times 184 minus y. And then I'm going to separate. So I'll move the dx to the other side, divide both sides by 184 minus y. And then on the right side, you have dx times x. Oops. Fix that. Okay. So then I can integrate both sides, and on the left you may need a u sub, so u is 184 minus y, so that your du will be negative dy, so dy is negative du. Okay. So I could rewrite this as negative du all over u equals, and on here this will be x squared over 2 plus c. Then you can integrate this guy. You can factor out the negative, and you just end up with negative ln absolute value of u. Let's go ahead and back sub. That would be 184 minus y. On the right-hand side, x squared over 2 plus c. I can exponentiate again and get rid of the ln and hopefully solve for y. What I want to be careful about, though, is that negative in front. If you exponentiate right now, the e and the ln won't necessarily cancel because of that negative. You would have to take the negative using the power rule of logs and bring it inside here, and then they would cancel. But the problem would be then you would have some fractions, and it would make your work longer. So my solution is just simply get that negative to the other side. So you have ln 184. And after you do enough of these, experience will kind of lead your hand. Again, this constant will absorb other constants. So you're not going to write minus c. You're just going to have a plus c. It's like a black hole. Okay. But you have to be careful that it won't absorb variables. Okay, now I can go ahead and exponentiate, and I can have 184 minus y equals e to the negative x squared over 2 times e to the c, right? Then you could drop your absolute value signs and replace it with a plus or minus on the right. And then I'm going to rearrange things on the right and replace it with a, so it normally be plus or minus e to the c. I'll just write it. X squared over 2. So you get 184 minus y equals a big C, e to the negative x squared over 2. And then you're going to solve for y. Okay, that was our ultimate goal anyways. So you get 184 minus c e to the negative x over 2, or you can let it absorb the, I think here you could just let it be plus. Okay, let's see if that works. So I get y equals 184, and they're forcing you to solve for y. So if you tried to think, oh, I could just leave it like this negative ln thingamajig, no, you're forced to solve for y. So anyways, plus big C e to the negative x squared over 2. Okay. Okay. So you know, some basic introduction to doing some differential equations. Now we can go ahead and introduce the growth and decay formulas. These are the simplest formulas and the most well-known in differential equations, but they're kind of unrealistic. It says in a lot of math modeling, you can literally just translate the phenomena that's happening into math speak, right? So if you know the rate of change of your population, is proportional to the population, you can turn that into a differential equation. Let's say dy represents the population with respect to time. That would be the rate of change of the population equals some constant k times the actual population. Okay, and this, you know, you could think of this intuitively, like if you have a bunch of fruit flies. Let's say in this petri dish you have like 2 fruit flies. In this petri dish you have a whole bunch more fruit flies. Okay, and which petri dish do you think the change in population is going to be greatest? Right? It's the second petri dish, right? It's the one with more people in it. That's what that phrase means. The rate of change of the population is proportional to the number of people in the population. If you only have 2 flies, you're not going to be pumping out hundreds and hundreds of flies, you know, but if you have hundreds of flies, then they're going to be procreating a lot faster. Okay, so that's it's an intuitive thing, and you're able to translate it straight into math speak. And then you could solve these things for our formula. So let's solve this for the formula for y and see what it is. So I'm going to separate, bring the y over here. I'm leaving the constant on the right. Integrate. So I get the ln of the absolute value of y equals kt plus c. And then exponentiate. So on the left, the e and the ln will cancel. You have absolute value of y. On the right, you have e to the kt times e to the c. Drop the absolute value. That will turn into a plus minus on the right. I'm going to change the order of e to the kt and e to the c. And then I'm going to replace the plus minus e to the c with a huge constant, e to the kt. I think in the book they presume that the population is positive, so they get around this whole issue of the plus minus. Okay, so if you read the proof of theorem 6.1, they've presumed, that's why you don't see the ln of the absolute value of y, and it's in this remark here. Okay. They presume that y is greater than 0, and if it's greater than 0, you don't need the absolute value. Okay, let's look at example 2, where they're using this idea in order to find an equation given some initial information. So again, the rate of change of y is proportional to y. So that means you're using this formula, y equals ce to the kt. Then they note some initial conditions. So I'll write them as ordered pairs, where we have t comma y in the ordered pair. So the first initial condition, 0, 2. And then the second initial condition is 2, 4. And then they want you to figure out the value of y when t is 3. Okay, so I'll put a question mark there. Okay, so there's a couple ways you could go about solving out, and what we need to do is basically figure out c and k, and then we could use this formula to figure out the unknown that we're after. Okay, so first I'm going to start with the initial condition here and just plop it into the equation. So I'll have 2 equals ce to the 0 times k. Anything times 0 is 0, so we just have 0. That will be 2 equals ce to the 0 is 1. So c is 2. And now I can rewrite my equation as y equals 2e to the kt. Okay, now I want to solve for the constant k. So the first step, I got the c value. Now I want the k value. And I could use the second initial condition to do that. So let's try it. I have 4 equals 2e to the 2k. And then I have an exponential equation and I need to solve. So divide both sides by 2. I get 2 equals e to the 2k. Take the natural log on both sides. So I have ln 2. On the right side, the ln and the e kind of cancel each other out again because they're inverses. So you're just left with 2k. And then you can solve for k, and that's equal to ln of 2 all over 2. Okay. So now I can rewrite my equation again. So I'll plop it into there, and I get y equals 2e to the ln 2 all over 2t. The book uses an approximation. I hate approximations, though, so I just avoid it altogether. Okay, so now I need to figure out what is y of 3. So I'm basically plopping 3 in for my t value. That's this last thing I need to do. Okay. So y of 3, what is that? That's 2e to the ln of 2 all over 2 times 3. And I need to put that in my calculator, which I will find in my calculator. 1 second, please. I just want to make sure I get what the book gets, right? So clear 2 e to the ln of 2 divided by 2 times 3 equals 5.6 something. Okay, so let's see what we get. I'll go to 3 decimals probably. Usually in the homework they'll tell you how many decimals they want. 5.657. Okay. Do they want you to? No, they just wanted you to answer that question. Okay. So of course we could go ahead and graph it if you want. One application of this kind of thing then is in radioactive decay. So example 3. They'll give you some beginning information and you kind of have to figure out the unknown. So they're giving you the initial condition is 10 grams of plutonium-239. 10 grams are released in a nuclear accident. So at time t equals 0, we have 10 grams. And then they want to know how long it takes for the 10 grams to decay to 1 gram. So it's like t equals what to give you 1 gram. You can kind of set it up in a little table if you want. We need to know the half-life to pull this off. So it says in a conventional nuclear reactor, 1 kilogram. Well, that's not the half-life. Well, how the heck am I? Oh, they give the half-life in a table up here. Okay, sorry. So what are we doing? It's plutonium. So it's 24,100 years. Life is 24,100 years. Okay, and then we could use these as kind of ordered pairs. This thing and this thing. And then solve for the unknown parts, just like we did in example 2. And then we could get our answer, okay? Okay, so first we're probably going to have to go after C. So again, my formula is going to be y equals c e to the kt. I'm going to use this first initial condition to get C. So when t is 0, y is 10. So c e to the 0 again. So c is just equal to 10. And then I could rewrite my equation as 10 e to the kt. Now I need to figure out that constant k. So now I'm going to use this other kind of condition. Okay, so when it says the half-life is 24,000 years, that means 1/2 of the initial amount. So 1/2 of means to multiply the initial amount, which is 10, will be left over in 24,000 years. So when t is 24,000, you should end up with 5 grams. Okay. So what? Well, this is going to allow us to solve for k. All right. So anyways, you could divide both sides by 10. You end up with 1/2. And again, you have an exponential equation that we can solve by taking logarithms. So on the right, then ln and the e's will cancel, and you just get 24,000 k. Then solve for k, and you get ln of 1/2 all over 24,000. And again, I don't like to really do the approximations because you see that thing is 5 decimals that you need at least for your model. So I'm just going to put the k in as is and write y equals 10 e to the ln of 1/2 over 24,000 times t for my official decay model. Okay, so now they want to know how long does it take for you to end up with 1 gram. So I'm plugging in 1 for y, and that will equal 10 e to the ln of 1/2 over 24,000 t. And yeah, so I have another exponential equation, move the 10 over. Take the natural log on both sides. So on the right this time, the ln and the e cancel. And then I just multiply by the reciprocal of the coefficient in front of t. So I'll end up with 24,000 ln of 1/10 all over the ln of 1/2. And then I'll go to my calculator and get the answer. So 24,123 times ln of 0.5 or 1/10 divided by the ln of 0.5 if you want, 1/2 if you want to be careful. And I'm getting 79 thousand. Their answer is so much different than mine. It's probably because of the approximation they've done. Okay. I'm just thinking. Would it really make that big of a difference? Well, it did. Yeah, so my answer is way off because I didn't do approximations. My answer is probably better. 79726.3 years if you want. So 79,000 years. It's awfully close to 80,000. Then the remark in the book, sometimes it's easier if you're doing things in your head, I think. You could use these other rules. We're not going to bother with that. I'm just worried about my answer. Oh, I see. I miscopied the, it's 24,100. Okay, so my answer is probably off then. I could fix that really quick, just put a 1 here, and then I'll probably get the answer they got. Let me see if that does the trick. Sorry about that. Just miscopied it. Little mistakes can lead to big failures if you're an engineer, so you need to be very careful. Now I'm getting 80,058, which is probably what they got. Yeah, so 80,000, but I'm getting 80,058 with no 58. So 58 without rounding. So there's probably some rounding error in there. Let's just go with what we got. Okay. So anyways, this was a decay problem, and of course the section is called growth and decay. If you could also model growth. Here we didn't see it explicitly, but the K value, if you look in the book, was actually negative. For growth models, the K value will be positive. Okay, so let's take a look at example 4. We have an experimental population of fruit flies. Follows this model. After 2 days, there's 100 flies. And 300 after the 4th day. So they give you some ordered pairs. You should be able to use that to solve out for your unknowns. The way they solve it is a little weird. So let's take a look. Y equals C e to the kt. They're going to plug each of these ordered pairs in, and then they have kind of like a system of equations or something, I guess. So let's drop them in, right? So it's dropping in this, we get 100 equals CE to the 2K, and dropping in this, we get 300 equals CE to the 4K, all right? Then you can take that first equation and solve for C. So you get C equals, you divide both sides by e to the 2k, or if you'd rather multiply both sides by e to the negative 2k. That's the same thing as dividing. So you get C equals e to the negative 2k times 100. And then we could plop that expression into here. So you get 300 equals e to the negative 2k times 100 times e to the 4k. Let me put the 100 at last. And then you could combine these two using our rules of exponents by just adding the exponents. So you get e to the negative 2k plus 4k is e to the 2k times 100. And then we could solve for k. All right. So that would give you 3 equals e to the 2k, and then k, take ln on both sides. So you get 2k equals ln 3, and k equals ln of 3 all over 2. Okay. What are they looking at? They want to know how many flies were in the original population. So to find the original population, it seems like you could just plug that in for k into the constant c. Because the c is, if you think about it, y equals c e to the kt, the c is going to always be the initial value because you're plugging in 0 for t, so y would be c e to the 0. And yeah, so c would be the initial value. I don't think that's what they do, though. What they do is kind of, let's see if we get the same answer just by plugging in that k value. So c would be e to the -2 times ln of 3 all over 2 times 100. So c equals e, the 2's cancel, and you get negative ln 3 times 100. And then you get c equals, you can use the power rule of logarithms to bring that negative inside that logarithm. Get 3 to the -1 times 100. And then cancellation laws for inverse functions. C equals 3 to the -1 is the same as 1/3 times 100. And that seems like the same answer they got. So C is approximately 33. 100 divided by 3 is 33.33 repeating. So yeah, about 33 fruit flies. So there's more than one. I think the moral of this story is there's more than one way to kind of skin your cat, so to speak. Okay. Let's go ahead and skip the declining sales problem and zip into the Newton's law of cooling problem. So this Newton's law of cooling is a lot like an exponential growth model. So let's give it a different section title. Newton's law of cooling. And basically you could think of it as kind of like maybe if you worked in a Marco's or something, it's like a pizza place, you could say, once you take that pizza out of the oven, you want to know how long until you have to throw away the pizza. You could use Newton's law of cooling to figure that out. Newton's law of cooling basically says that the rate of change of the temperature, so we'll say y is temperature, of the pizza is proportional to the difference between the temperature of the pizza and the temperature of the room. So we'll just say T sub R or something. Usually they say T sub M for the medium, the surrounding medium. Okay. So if it's really cool, the rate of change of the pizza will be very high. And if the room is kind of hot, the rate of change of pizza won't be so drastic. Okay. Let's look at example 6. So what are we doing here? Let y represent the temperature of an object in a room whose temperature is kept at a constant of 60 degrees Fahrenheit. So our differential equation should be k times y minus 60. They give us some initial conditions. So the object cools from 100 to 90 degrees in 10 minutes. So the original temperature is 100, and then after 10 minutes we get 90. How much longer will it take for the pizza or whatever object it is to, well, a pizza would be a lot hotter. How long will it take for the object to decrease in temperature to 80 degrees? Okay, first off, we got to get the equation. It's not going to be the same as y equals c e to the kt, but it's very similar. We're going to separate and solve for it right here. Okay, so dy all over the y minus 60 equals k times dt. Integrate, so ln absolute value y minus 60 equals kt plus my integration constant. Exponentiate on both sides, and you get absolute value y minus 60 equals e to the c times e to the kt. Drop the absolute values, replace it plus minus, And then finally replace the plus minus with a C and move the 60 to the other side. So it's basically just the exponential growth equation right here, but then you have to add in this room temperature of plus 60. Okay, so I'm going to use my initial conditions to solve for C and K. So let me recopy my initial conditions. This time the C value is not automatically 100. So you'll see here, if I let the temperature equal 100 and let time equal 0, I get C times e to the 0, which is 1. So you just get C plus 60. And so the constant C is actually 40, not 100. Okay, so I'll rewrite my equation as y equals 40 e to the kt plus 60. Then I need to solve for this constant k. So again, I go back to my ordered pairs. I'm going to use the second ordered pair now. So 90 equals 40 e to the kt plus 60. Move the 60, so I get 30 equals 40 e to the kt. Divide both sides by 40, so I get e to the kt equals 3/4. Take logs on both sides. On the left, the ln and the e cancel, you just get kt. On the right, you just get ln 3/4. Solve for k. So what was t? T should have been 10, so I should have a 10 for t. So I'll just rewrite it now as ln 3/4 over 10. Okay. I forgot to put the 10 in for t. Okay, so now I can rewrite my equation officially as y equals 40 e to the, and this should be a 3/4, e to the ln of 3/4 all over 10 times t plus 60. And ultimately, we wanted to know how long does it take for the temperature to go to 80 degrees. So you plug in 80 for y, and then we're solving for t. Okay, so another exponential equation, move the 60 over, 20. Divide both sides by 40, so you get 1/2. Take ln on both sides. And then divide both sides by, multiply both sides by the reciprocal of ln of 3/4 over 10. So you get t equaling 10 ln of 1/2 all over ln of 3/4. Okay, and then let's get an approximation. 10 ln 1/2 divided by second ln 3/4. And it looks like about 24 minutes. I think we were in minutes, right? Yeah. Let's see if that's what they got. Yeah. Okay, great. They do a lot of graphing here. I'm sort of avoiding the graphing, but you can always go to the Desmos and kind of see what you got. So that's Newton's law of cooling. And then they just have some exercises. So let's go into the actual exercises and see what we're dealing with. Rate of change of n is proportional to n. So this number 6, I guess, kind of take a look at that real quick. dn over dt, the rate of change of n, that's just the differential equation for the growth, okay? Equals n times is proportional, so k, you need a constant k. Make sure you're putting in a capital N when you do put in your answer. And then this will be, obviously, c e to the k, c e to the kt, depending on if they want you to write it with the constant k in there without solving for k and c. Evaluate the solution at the specific value of the independent variable. So we need to figure out what n of 3 is. They give us an initial condition. And of course, our our n of t is equal to c e to the kt. So I think this is pretty straightforward. They want to know what happens when t is 3. So plugging in the initial condition, 250 equals c e to the 0, so just c is 250, so our formula becomes 250 e to the kt. Then I want to go after the k value, so we'll use the second initial condition to the k times 1. So e to the k equals 40 over 25. What is that? That's 8 over 5. Take ln on both sides, so k will equal ln of 8/5. And then we could rewrite our equation, n equals 250 e to the ln of 8/5. And we want to evaluate it at 3, so plug 3 in there. And let's see if we nailed it. 250 times second ln 8/5. Oops, I forgot the e thingamajig. E to the ln 8/5 times 3. Oh, really? 1024. That can't be right. I don't know, we'll see. Yeah, that's right. Okay. These are the kind of fill in the blank problems. Carbon 14, let's try this one. 9. Carbon 14 assumes that carbon dioxide on Earth is today the same radioactive content as it did centuries ago. If this is true, the amount of carbon 14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon 14 absorbed by a tree today. A piece of ancient charcoal contains only 45% as much of the radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal? And the half-life is 5715. Okay, so what is true? So I've been thinking. So I think to think about this for a second. I think though that we could just kind of first find a k value. So the half-life is saying, you know, in 5,715 years, only half the initial amount will be left, right? So we have 1/2 c equals c e to the 5715k, and that allows us to solve for k at least. Divide both sides by c, you get 1/2 equals e to the 5715k, ln on both sides. So you get 5715k equals ln of 1/2, and then solve for k, ln of 1/2 all over 5715. And then we note that only 45% of the carbon is left in this particular case. So 45% of the original amount of carbon is left in t years. So we could set up our formula to solve for time, I believe, because now we know k. So you got ln of 1/2 all over 5715 times t. Divide both sides by c, you get 0.45 equals e to the ln of 1/2 all over 5715t. ln on both sides. So these will cancel. Ln of 1/2 all over 5715 equals ln of 0.45 times t multiplied by reciprocal. T equals 5715 ln of 0.45 all over ln of 1/2. Let's see if that does it. If not, I'll try something else. 5715 times ln of 0.45 divided by second ln of 1/2. 6583, 6583.698, 2 decimals, so 6583.70. Oh, round to the nearest year, so 6584. 84, which kind of makes sense because after almost 6,000 years, half of it's gone, and this is more than 6,000 years. So probably like you're going to get like 55% of it gone. Oh, hey, we got it. Okay. Let's see if there's anything else I need to look at. These are cooling problems. I think we'll call it quits there. As usual, well, I didn't do, let's make this last problem the video quiz. I apologize. I always forget the stupid video quiz. So this one will be the video quiz number 9 from WebAssign. So you can pause the video, copy that down. That'll be the quiz du jour. Okay, I want to make sure I put it in my notes. Video quizzes for 1620. These two. So this would be the first and the second set of video quizzes. Okay, thank you for watching, and I'll see you next time.